So we had a couple of our speakers already present to provide that big overview idea of environmental flows and functional flows. What are the elements of functional flows? That provides the basis for us getting down into a little bit more of the nitty-gritty of potentially regional applications as well as site-specific. And so each of our speakers is going to have a little bit of a different slant in terms of drilling down into what we heard in those first two presentations. So the first speaker is Eric Stein, and he's the one who moderated the earlier session, so I don't think he needs any introduction, but I'll let him get into it. He's going to be talking about more of developing flow targets, but using BMI data, so that benthic macroinvertebrate data, and how do we use that in Southern California to develop some flow targets in that type of environment.
Great, thanks, Erin. So you heard, right before the break, you heard Julie and Sarah talk about the framework and the tier one, sort of the statewide perspective on environmental flows. And so now we're going to come down into that tier two that Julie talked about. I'm going to give you an example from Southern California where we don't have salmon. Well, we do, that's not totally true, but what I'm going to be focused on is not related to sort of managing salmonid species. And then I'm going to be followed by Robert Holmes, who's going to talk more about the work that they're doing that is more related at the tier two as it relates to some of the fish species. So with that. So again, just to reiterate, I always start with the slide because, I like to remind people that hydrology is the sort of master variable that we're dealing with in a lot of these systems. And if we can manage the hydrology effectively, oftentimes it gets us pretty far down the roads towards protecting stream health, knowing that there are geomorphic and chemical moderating factors, but hydrology is really important. And so we really always like to start by thinking about how to manage the hydrology to protect those biological endpoints that we're most concerned about. So Julie showed you this graphic in terms of this idea of trying to understand the relationship between how changes in flow relate to changes in biology and finding that sweet spot or that zone that we want to manage at. And so what I'm going to give you an example of in the next 10 or 15 minutes or so is how we sort of define this type of curve for Southern California based on the issues that are relevant for the systems we're managing in. And so when we think about this sort of tier two that you heard about, we have to think about some basic starting points for our analysis. So we have to think about what types of streams we're working in, what types of ecological endpoints, and what type of management needs. So in Southern California, we're dealing with intermittent and ephemeral streams primarily, and so those are the stream types that we're focusing on. I'm going to talk about benthic macroinvertebrates as our ecological endpoint, again, because in a lot of what we're dealing with, the big drivers are water quality programs that use benthic macroinvertebrates and now stream algae, but I'm going to focus on the invertebrates today as kind of the driver for understanding kind of the health of the system from a water quality perspective. And again, we do have dams in Southern California, but they're sort of different types of dams in some ways, and they're not the same types of issues as it relates to some of the fish species. So most of the drivers from a management perspective have to do with managing urban runoff. And in the past, that had been excessive urban runoff, as you heard about from some of the morning speakers. Now we're actually moving back towards reusing or capturing and reusing some of that runoff. And so again, how do we strike that right balance to make sure we're maintaining the stream health that we're interested in? And so the specific approach, again, Julie mentioned this, the specific approach that we used in terms of the tier two method that we applied for Southern California is this ecological limits of hydrologic alteration. And I'm going to just walk you through the basic steps associated with it. And so this is an approach that, again, is a very data-driven approach. So it's a slightly different than the functional flows approach that Sarah talked about. So the first step in this ecological element of hydrologic alteration, so the HA part, the hydrologic alteration, is we have to be able to figure out for any given stream what is the degree of hydrologic alteration relative to some unimpaired condition. Once we know the degree of hydrologic alteration, we need to be able to relate that hydrologic alteration to some sort of response in the biological community of interest. In our case, it's benthic invertebrates. It could be fish. It could be algae. It could be riparian habitat. There have been studies in various parts of the country that have looked at different endpoints. For our application in Southern California, it's benthic invertebrates. And then we have to try and develop some targets, some numeric targets based on this relationship between hydrologic alteration alteration and biological response, and we use that to kind of set numbers that we want to manage towards. And one of the benefits, and one of the reasons we use this for the Southern California region is it really is designed to be applied at a regional scale versus sort of a reach-specific or a stream-specific scale. And so for our application from a water quality perspective, the regional scale is a really attractive method, part of this tool. And so again, then we can evaluate this to look at the specific management actions. All right, so I like to start with this slide because, as I mentioned, this is a data-driven approach, which means you need data. Right. So, and we're very fortunate because the state of California in general has invested heavily over the last 15 years or so in developing, in my opinion, what are some of the best bioassessment data sets in the country. And so when I go into other parts of the country and I talk about, the density of data we have in the state, people are like drooling on the table, right? Because we actually we're very fortunate in this state that we have the investment in that level of data. And so this map shows our Southern California Regional Monitoring Program and a lot of the sites where we've collected bioassessment data over the last 7 or 8 years. And this bioassessment data that we've collected really is the engine that drives our ability to develop these regional relationships between flow and biology. So that's really the starting point. So really what we want to do to develop this method is for each of those dots on the map where we have biological data in the form of our Benthic invertebrate index, which is the California Stream Condition Index, we want to be able to assess the degree of hydrologic alteration at every one of those sites. There's about 800 of them in Southern California. Now the problem is we know that very few of these sites are gauged. So we need a method to try and evaluate hydrologic alteration at basically 800 ungauged sites in a somewhat parsimonious manner. So as you heard this morning, that leads us to models, right? Again, all models are wrong, as you heard, but we have developed an approach that we think is useful for the specific application that we're trying to apply here. And so really what we want to do with the hydrograph that you can see on the screen here is we have sort of our current hydrology, and we want to be able to model or estimate what is the current hydrology. And then we want to be able to then in the model simulate what that specific location would look like under reference conditions. So we can use a very traditional rainfall runoff type of modeling approach, and we can estimate the current hydrology using that approach, and then we can go into the model and essentially turn it natural. We can change the land use, we can change some of the routing factors in the model, turn it natural, and simulate what that location would have looked like under natural conditions. So the difference between the blue and the yellow hydrograph, so again, I went to UCLA, that's why they're blue and yellow. All right, so in full disclosure, right? So the difference between the blue and the yellow hydrograph, that's really the degree of hydrologic alteration, and so that's how we get that. Now, we don't really want to be able to, we don't have the resources to do this for 800 individual sites or to spin up 800 models. So we created what we call a model ensemble, and that's the graphic that's shown in the map there, which is on my right. And so the ensemble approach basically means that you just develop a set of models. We developed about 30 of these models that represent the ranges of watershed types that we have in the region. So some big watersheds, some small watersheds, some steep, some shallow. So about an ensemble of about 30 models that represent the range of watershed types. And then we have a statistical tool that allows us to basically go into any site of interest, and based on the physical properties of that watershed, its elevation, its slope, its basic rainfall patterns, we can pull the best matching model out of our library and apply that best matching model from the library to that specific site by just tuning a very small number of parameters. So it just creates a very efficient way for us to use this library of models and apply them to hundreds of sites in a very efficient way. And so that's the concept of the model ensemble. So we did that and then essentially applied that approach to all 800 of our sites where we have bioassessment data. And what you get out of there is you get a time series of daily flow data. You could do it hourly. We did it daily because that's really all the resolution we need for this analysis. So we produce hourly flow data for a number of years from all of those sites. And then we can generate a whole series of metrics, literally hundreds of metrics that relate to magnitude, duration, variability, different elements of the hydrograph. And so what we want to be able to know is which of those hundreds of metrics are the most important ones for the biology, which ones have the best relationship with biological response. So we generate these hundreds of metrics, and we generate them for different climatic conditions, average years, wet years, dry years, et cetera. So we have this whole sort of huge databases of metrics, and now we have to go through sort of a metric screening process to understand which ones have the best relationship with the biology. And so the way we do that is we use an approach called logistic regression. And so the reason that I personally like logistic regression is because it's a probability-based approach, which means as a scientist, I don't actually have to make a decision. I can push that off to the managers or the regulators. And the way this basically, this logistic regression approach works is on the y-axis I have the probability of the CSCI score being below a given threshold. And so we use 0.79. It's on a zero, the CSCI goes on a 0 to 1 scale. And we use 0.79 as sort of a boundary between impacted and more natural. And that's kind of a putative boundary that we tend to use. So I can look at the probability of the CSCI score being sort of good, being above that 0.79 level, and I can relate that to any hydrologic metric that I want on the x-axis. So in this example, I've used hydration flow is my example, but it could be any one of those hundreds of metrics, and I'm showing it in sort of the decreasing direction. So these things can, these metrics can go up or down, and you look at them, and the responses are different whether they're going up or down. So this happens to be one metric in the decreasing manner, and then I can just look at the 50% probability of achieving that sort of good score, and I can look at how much my hydration of flow has to decrease before I sort of drop below that desired threshold. And so in this case, I can say if I lose about 7 days of if my hydration flows are decreased by about 7 days over the course of a year, then I have a 50% probability of causing a problem to my biology. There's nothing magic about 50%. You could decide at 75% or 25%. That's why I like these curves, because you can pick where you want to be on the y-axis and set the target based on how risk-prone or risk-averse you might be. Or on, based on the quality of the stream or other constraints like the questions that came up. Maybe I have other constraints in the system like water supply or things like that. And so then we go through a screening process. We do this for, all 800 of those. We do it for all the sites. We do it for all the metrics. We've got hundreds and hundreds of these logistic regressions. And so we look for the ones that have the best relationships with the biology. We look for ones that represent different ranges, different parts of the hydrograph, duration, frequency, timing, things like that. We minimize redundancy, and we look for metrics that we can actually manage. Right, a metric's not very useful per se if you can't do something from a management perspective to actually change it. And so we run through all those filters, and we come up with a table that looks like this. This is an example of a table where after that whole filtering process, we can now have a set of priority metrics that we can assign sort of thresholds to and say, well, if we, either depending whether it's an increasing or a decreasing threshold, if we're above or below that number, we think that that's going to be problematic in terms of the biology. And so we can create these tables based on different biological endpoints that allow us to then manage. And so that's basically, let me go back for a second. So that's basically kind of the end product of all this analysis is this sort of set of numbers. And so then we can apply these numbers in different sorts of ways. We aggregated those 7 metrics into an overall index, and so we can look at across our region where the different degrees of hydrologic alteration are. We can go into specific watersheds, like this example, and look at the current degree of hydrologic alteration by catchment, which is the top map, and then we can overlay projected land use change based on the county's general plan, and look at where we think we might see a decline in the hydrologic condition. So we can see areas of the watershed where we think, based on future land use projections, where do we think we might have more problems in the future, and maybe target our BMP application or management applications to those specific areas. We can also then combine, in this is the same watershed, we can look at combining where we have hydrologic alteration with where we have either good or bad biology or other indicators of water quality problems. And we can create this little matrix and say perhaps areas where we have poor hydrologic condition in terms of a lot of alteration and poor biologic condition, those might be the priority areas for managing flow, whereas in some of those other boxes, if we have, say, poor biology but good hydrology, that might be a candidate where maybe flow is not the problem, maybe it's something else like a chemical problem, and we might look at a different management prescription there. And then finally, where we have good biology and good hydrology in sort of that lower right box, that might be those areas we prioritize for protection and try to make sure that they stay healthy. So again, we can use these combinations to prioritize management. And then finally, we can do some scenario analysis. And so this is an example of then going into a specific application in a subwatershed. This is the Alvarado Creek subwatershed in San Diego County. And we can look here and we can look at the current runoff, which is sort of that blue hydrograph. And there's about 50% impervious cover in this watershed. And we can simulate, if we want to get down to sort of and we look at that sort of 2%, which is kind of the base, that would be like a reference condition, would be about 2% impervious. And we can basically ask the question, what type of BMP implementation do we want to impose on the system in order to get those flow metrics down to a level where we're going to sort of have a high level of confidence that our biology will be protected? So using those metrics, let me go back a second, using those metrics that I showed you previously, I can create a table like this and look at some of those flow metrics, and I can say if I have a threshold, if I want to reduce my effective imperviousness by implementing different types of BMP or low impact developments, how much do I have to reduce my my effective imperviousness before I get to get those metrics down to a level where they're going to be protective of the biology? So again, in this case, we can see that in many cases we need to get down to 5 to 2% effective imperviousness before we manage the runoff to a point where we're protecting the biology. But we can use these types of scenarios and models to sort of say, how much BMP implementation do we need to get to the targets that we want? All right, so that's kind of a quick run through of sort of a case study of how we developed one of these tier 2 methods for Southern California, where urban runoff from developed land surfaces and benthic invertebrates are the main issues that are driving our systems. And so in the future, obviously, we want to continue to use this approach to look at other biological endpoints, such as algae, or in some areas where we do have fish or riparian habitat. We want to improve our ability to kind of tease out flow versus other factors in terms of what are the driving factors in terms of the management. We're very cognizant that we have this issue of shifting baselines. We have changing rainfall patterns associated with increasing wet and dry cycles, long-term climate change. So we have to be able to think about how those changing baselines might affect some of our management targets. And then obviously we want to incorporate all of this into those larger frameworks that Julie and Sarah talked about earlier. So I had another version of this. So let me just, I had a slide. This is version control at the last minute. I did have a slide in here that talked about data, because this is a data science symposium, but I'll just verbally tell you what that slide said. And it basically said that the long-term goal, and Greg has already alluded to this, a lot of this data is already available on data.ca.gov. Some of the maps that Julie showed are available through some of the SWAMP websites, where you can overlay them with bioassessment data. So the idea is, as we develop these data tools, we're trying to make them available for people to download and play with and use for their applications.